Hello everyone, thanks for joining the event, and I'd like to welcome you to the virtual live stream as part of our Future Ray experience at ITS World Congress here with our Sensors for Ray train. My name is Katharina, I'm an expert for project management from Deutsche Bahn and your host for today's stream.
My name is Ruben Schilling, I'm the perception lead at Digitale Schiene, and I will be a presenter for this virtual tour.
So what is Sensors for Ray? The Sensors for Ray project is a joint research and development project from Deutsche Bahn and our partners Siemens, Bosch, ibeo and HERE Technologies. And today we will demonstrate the project results and show you how this perception and localization technology that is currently used in automotive can actually be used for rail, and how the sensors take over environment perception, relieving the burden on humans. And what are you going to experience in the stream today? So the test train of our Sensors Array project will soon arrive in Hamburg Bergedorf, and in a few minutes the live animation starts for our guests at the ITS and for you here in the live stream. And before we start with a short keynote from our head of railway digitalization, followed by an explanatory video of our Sensors for Rail project. And afterwards, the live animation starts, in which you will experience live what the train already sees and perceives, and my colleague Ruben will take you through the live animation. And in the end, we will have some time for Q&A, so if you have questions during the presentation, please use the chat. And if you like, you can also write in the chat from where around Germany and the world you are joining today's stream. And we will now see a keynote from Annika Hundertmark, our head of railway digitalization, who will briefly introduce Digitale Schiene and explain how sensors for rail fit into the overall initiative.
Yes, hi, my name is Annika Hundertmark, and I'm responsible for railway digitalization within the program Digitale Schiene Deutschland of Deutsche Bahn. I'd also like to welcome you very warmly to this live event. I'm sorry for not being live here, but I have a very good reason for that, because currently I'm boarding the train in Hamburg Bergedorf. So nevertheless, let me please use this opportunity to give you a short explanation of what we are doing and why we are doing this. So let's have a look at one of our most challenge of today's times, which is the climate change. And to be honest, it's at some points in life very easy to protect the climate. Just take the train. The modal shift of transport to railways is very important. And of course, it needs a basis. It needs, for example, enough trains, so a very good offer to the customers, being it people or also goods. We need to have very good quality, and we need to offer the service to a very good price. So these are the main targets of Digitale Schiene Deutschland. We would like to enhance capacity, quality, and efficiency of the system. So how do we want to do this now? What is our target picture, our approach? Let's have a look at this. So first of all, it's important to understand that if we want to change something, we need to take into account the whole, like railway production, which is infrastructure, vehicles, and also the controlling level. But let's now come to the target picture. We think it's very important that in future we have a railway system in which trains run automated and sensor environment. Trains run in optimal distance, so headway is the distance between two trains, and that the trains in the network are steered and managed optimally throughout a traffic management system. And how do we now realize this target picture? So what is the approach? We have like two building blocks. One building block is the system architecture. We need to have a system architecture which describes the overall system, its elements, its users, and how the different things fit together. So we're talking about functionalities, we're talking about interfaces, and so on. And it's also important to align on this with other European partners on European level, because we know that railway business is a European business. And the second big building block is that we work with technologies. Technologies are, of course, very important to us. Yeah, let's have a look at our most important technology clusters. So if we start on the left-hand side, you see AI. Artificial intelligence is, of course, of high importance to us. For example, we are using the approach of deep reinforcement learning when it comes to the capacity and traffic management system. And you can imagine that for everything we are doing, a very solid and high-performing communication base is needed. So therefore, we are very active on everything connected to 5G and the future railway mobile communication system. If you want to make sure that the trains can run an optimal distance later on, we need to enhance the signaling technology. And we are doing this, of course, based on the European standards ETCS. On the right-hand side, you see automatic train operation. This comprises everything which is needed so that the train can afterwards accelerate and brake, for example, automated, or that the doors can open and close automatically. And now let's come to the technology clusters used within sensors for rail. As the name says, sensors for rail, it's mainly sensors which are of importance here. So we have different types of sensors. First of all, we have sensors which perceive the environment, like cameras, radar, lidar. Then we have sensors which are relevant for localization, for example, GNSS. And we have a third thing, the digital map, which comprises all relevant information which is needed to realize what we'd like to see with sensors for rail, which is, for example, a landmark-based localization and also the environment detection. And you can imagine that everything we are doing there is connected to data. So we need to collect data, we need to process data, we need to transfer data, and also we need to store data in the end. And therefore, computation is important. And yeah, therefore you see here this cloud icon. And of course, as everything, we also need to take care of IT security. Yeah, this was the overview of Digitale Schiene Deutschland, our approach, our goals, our technologies. And now I wish you a very nice live event. I'm sure you will be thrilled afterwards. And yeah, have a nice day and see you the next time.
Thanks to Annika. So our test train is just running into Bergedorf station for the trade show guests. And you can see the train now on the screen, how it looks. And in addition, you can also see on the right-hand side a picture of the interior of the train, so you get a good idea of what is happening live and where you would be sitting if you were in Bergedorf right now. And a few minutes are left before the virtual ride with the Sensors for Rail train starts. And until then, we will show you a video that briefly summarizes our project for you and introduces the technologies. And in the film, you will also see how this train that you're seeing now was equipped. So starting today, the results will be presented to the public for the very first time. So this means you are part of a premiere. So sit back, relax, try to imagine you would be sitting in our Sensors for Rail test train in Hamburg. It's showtime and have fun.
Less traffic, less congestion, and fewer harmful emissions on the road. More passenger transport and freight traffic on the railway. The future of mobility is rail. The sector initiative Digitale Schiene Deutschland creates more capacity, reliability, and efficiency for the railway system without building a single new track. The foundations for this are laid with the radical modernization and digitalization of infrastructure. On this basis, intelligent future technologies continuously get integrated in the rail system. A future project that Deutsche Bahn implements together with several industry partners as part of Digitale Schiene Deutschland is Sensors for Rail. The goal, to equip trains with comprehensive sensor technology for environmental perception and real-time localization, enabling even tighter scheduling of trains. This enables higher utilization of the rail network. The challenge, the combination and integration of various technologies from completely different industry sectors in the rail system. 5 partners have joined forces to tackle this extensive research and development project. Deutsche Bahn provides the vehicle and the infrastructure. It also oversees system design, vehicle engineering, and conversion. Siemens leads the system tests and determines the highly accurate train front position using an advanced localization method that evaluates the motion data of the train. Bosch and ibeo supply the sensors for environmental perception and object recognition and fuse the sensor and localization data using intelligent algorithms. And HERE creates a digital HD map in 3D using high-precision laser, enabling the accurate localization. In the first step, the train is equipped with extensive sensor technology. Cameras, radar, and LiDAR systems on the front of the train detect dynamic and static objects on and near the track. In the second step, a high-performance computer fuses the sensor data to provide a reliable image of the train's surroundings, even after dark or in fog. It also recognizes the course of the tracks and puts it into context with current driving conditions and objects in its vicinity. In addition, it is possible to detect the position of the train relative to landmarks such as catenary poles, platform edges, or buildings near the track, and use them as a reference for the location of the train. This information is compared with the landmarks saved on the HD map and with the position detected by the Global Navigation Satellite System, as well as the evaluated motion data of the train to determine an accurate location to the nearest centimeter. The HD map becomes the digital twin of the track and enables a continuous comparison of the target and actual position of the train in its environment. Sensor-based environmental perception also helps swiftly and reliably detect obstacles and hazards in real time, so that the train can be diverted and any necessary maintenance measures taken. As a result, the localization and environmental perception data of the train can be used for safe and efficient traffic management on the railway. The Sensors for Rail project harnesses the full potential of the digital rail system. Innovative sensors, highly automated driving, and intelligent controls become the new normal on the railway. The first milestones have already been achieved. However, this is just the beginning of the journey towards the digital rail transport of the future.
Yeah, we hope you enjoyed the video, and the train ride starts very soon, and we will let you know when it starts. And Ruben, could you maybe get a bit more into detail and explain the hardware and software installed in the train and why we need the digital map and what is so special about it?
Yeah, sure. Thanks, Katharina. At the start of this project, we analyzed what the requirements are for a digital railway operation. And we came up with some requirements that led to a very powerful sensor setup for this perception system that we see here installed at the front of the train. So as you can see in red, there are 3 radars mounted on the corners, one each, and then to the center, there's another one. And you see 6 LiDAR sensors mounted in purple above the windshield. And then you can also see that there are 2 cameras installed to the front of the train. So this is a redundant setup that has up to 550 meters of range, which is approximately 300 meters more than you would find in one of the common driver assistance systems that you may know from road vehicles. In addition to this perception system, you can also see the installation of our real-time localization system. That has a GNSS antenna, it has an inertial sensor, it has a wheel encoder, a 4G LTE antenna, and a high-performance server. All of these systems are connected to a data logging system that is central in the train so that we can record data on our test rides. And we have a redundant setup on the other side of the train so we can both go in both directions with this train, forward or backward. You can see here the cones for the radar sensor. So those are horizontal field of views with up to 210 meter of range forward. For the LiDAR sensor, you can see 3 different cones that we are using the 6 LiDAR sensors for, and it reaches of up to 550 meters. And you see that the camera setup is actually redundant to the LiDAR setup. So that's also quite important. In addition to these sensor systems, we do have a digital map, and the digital map is really important as a complementary system to these sensor systems. So in the digital map, we have stored all the assets that the train usually encounters on a ride through our train network. You can see here a fly-through our digital map, and this map actually contains classified 3D objects in centimeter accuracy precision. So this map was pre-recorded before our ride, and it is stored to the train so that the other systems can access this data. Please mind that this is a research and development project, so we currently do not have any functions available that update the map as we are running live. So if there's any discrepancies to the real Hamburg route, that is because the map is a few months old to the point where we are presenting it right now. On today's ride, we will take the train from Hamburg-Bergedorf to Berliner Tor. And you can see this here displayed on the map. And we also have this navigation pane on the top of your interface. To the left, we have the functionality pane. And on the bottom left, you see a statistics dashboard. So later on, when we show you the functions, you can see the count at which we have encountered certain objects. So our train has been set in motion already. As you can see on the bottom left in the interface, we're running at about 50 kilometers per hour already. Our train is equipped with a perception system at the train front and redundant on the train rear to operate in both directions. And it's equipped with a real-time localization system that we'll introduce a little bit later. So in this overview, I would like to highlight to you that to give you the best experience for this virtual experience tour, we have connected this interface that you are seeing with the live data from the train. So you can already see here the first function that is displayed, which is on the left side. You have this function panel. We're running the landmark detection function right now for you. And this is the live data that you are seeing from our vehicle that's running currently in Hamburg. So in pink, you can see landmarks that our train detects with the perception sensors. And this is complemented by a digital map. So the gray interface you see is a version of the digital map that is stored on the train. And we can detect these landmarks. As you can see in front of the train, we see pillars, and to the right, we can also see how our train is recognizing walls across our track. And this is quite good because these things are built in naturally into our physical infrastructure. They're just part of the track. And these landmarks can be used to compute a local position for the train. And I will tell you a little bit later how this is combined with other localization information. And this can be done without building any additional infrastructure along the tracks. And that's a quite big advantage because more precise localization is one of the key things that you need to increase the capacity on our rail network without building new tracks. And in cities like Hamburg, it's very difficult to build an additional track. And so this allows us to just use what is already there to improve our localization. So this function was developed by our partner, ibeo, using their LiDAR sensors. I'd also like to highlight that there's a partner stream from ibeo coming up on Thursday. So if you're more interested to get more details on the LiDAR sensor, you can join their stream. The map that you can see in gray is provided by our partner HERE Technologies, who've basically pre-recorded this map using laser scanners and a very highly accurate reference positioning system so that we can really get this map down to a centimeter level accuracy and then measure these landmarks also with centimeter accuracy with the LiDAR scanner. So a LiDAR scanner is a laser scanner that just not has a single laser beam, but that fans out this laser. So in this case, we have 6 LiDAR scanners on the train front building up a different field of views, and that allows us to measure with centimeter accuracy. So our next function is the train detection we would like to show you. When our train encounters a train, you see this blue quadric in the picture-in-picture. So we will show you other trains that we'll encounter during our route with this blue quadric. So our train can detect other trains, and we are just focusing here on the S-Bahn traffic, as this project really revolves around the S-Bahn traffic. And this is a function that was developed by our partner Bosch, using all three sensor modalities for perception that our train is equipped with. So we have a redundant setup of cameras and lidars that have about 550 meters of range. And we do have also radar sensors equipped to the train that extend to the front more than 200 meters, and they also extend to the sides of to both sides of the train. And using all these sensors, we are detecting other trains. So this is an important functionality, as in rail operation, there's a common maneuver to couple and decouple trains. And in order to facilitate something like that, we would have to be able to perceive another train to allow us to move as close to another train that we can actually couple or decouple these trains. And our train hence can do this automatically, so to detect these other trains, which is the basis for further automation. The next function we would like to show you is pedestrian detection. So this is obviously the other very common moving object in the railway system. So pedestrians, may it be passengers waiting on platforms, or may it be workers in working zones. Pedestrians are also common. And our system is also able to detect pedestrians. I would like to emphasize that we only detect pedestrians. We do neither recognize nor identify passengers, and we also have no plans in doing so. So we just are interested in the fact that there is a person present and in the location and movement of that person. We have no further interest, and our system can detect these pedestrians using LiDAR and camera sensors. So there's an artificial intelligence on board that was trained for this task. And our partner Bosch has developed this functionality. And here you can see that we are also colorizing pedestrians as we are entering the station Mittlerer Landweg. You can see this on the navigation bar in the top view. You see the current live view, and you've seen that there's a few pedestrians on our platform. And the platform has a semantic layer that allows us to color these pedestrians in green for those waiting in waiting zones, and in yellow for pedestrians who stand closer to the border.
And everyone who has just joined our stream, this is a little reminder that we are actually live. So we are streaming from the Sensors Array test train in Hamburg right now, leaving Mittlerer Landweg.
Thanks, Katharina. And another functionality we would like to show you is the track detection. You see this as the red path extending on the front of the vehicle. And you see there's a number that jumps. So you can see we have up to 550 meters of range here, which is exactly matching our camera sensor design. So this is a function that is based on camera data developed by Bosch. There's an AI that was trained to detect the track course. And this is quite important. We also have this track course stored in the digital map, also with centimeter level accuracy. In this way, we can measure our live data generated with the camera and the artificial intelligence to the pre-recorded map data. and hence verify that our infrastructure is exactly in the state that we would expect it to be when we're operating a train. And as you may know, our infrastructure is very well maintained, and there's construction rules, how we build our infrastructure. So this is a very reliable piece of our railway system, but here we can just verify that it's with every train that is equipped with a sensor system that it's in the state that we expect it to be, and how we also maintain it. This is the track detection function. We can also do this for other tracks. Here in this demo, we're just focusing on the ego track. And yeah, you can see this. This information can also be used for risk identification. So if there's an object close to our track, for example, we do have now the information where we are going, also geometrically, and can estimate any risks that other objects that are foreign to our system may pose to our traffic.
Okay. So we have learned quite a lot about static and dynamic object detection, and we are approaching Belwerder right now. So now you can see actually here everything what the train sees and perceives. And Ruben, could you tell us how we can localize the train and why we need it?
Yeah, sure. As I mentioned in the beginning, we have a real-time localization system installed to the train, and this consists, first of all, with the basis, the GNSS antenna. We also have a wheel encoder, similar to the traditional localization system. It also has a wheel encoder, but we also give a lot of the perception cues to the localization system. And all this is fused on a localization onboard unit. So there's a Fusion PC installed to the train that can basically combine all this data. And there's a big difference to the traditional railway localization here, because in the traditional localization, you drive over a so-called balise, that is a device installed onto the track. And the train has a balise reader and then reads basically its global position while it's going across that device. And so we need to install all these devices in order to locate the train. And this location information is then propagated using a wheel encoder. So that's how the classic localization works. Our system here has this global location using the GNSS antenna. So we have it as a continuous measurement all the time. And we combine this with also the wheel encoder, but also with these perception cues. And from the perception, you can see there's a radar position in red. There's a LiDAR position from the landmarks in purple. And then we can fuse this information to this green consolidated position. This was done by our partner Siemens, who are fusing all this information. So the red location is basically a radar information that was pre-recorded and stored in a map. So those are the radar reflections. And then our train can match those with the live radar data and then computer position, similar to how this is done with landmarks and LiDAR. Now, the last function we would like to show you is the occupancy detection. And you see in the small window a tree that could look like this when it's detected in a so-called occupancy grid. So an occupancy grid is a virtual grid that we span in front of the train. And so we have discretized the environment in really small cubes. And our LiDAR sensors can measure whether this kind of space is occupied by something or whether this is free. And obviously, in the railway system, we maintain the so-called clearance gauge. This is this green virtual tunnel that you can see in the presentation. This is maintained by construction and by maintenance to be free of any obstacles all the time. And our sensor system, as you can see, can measure these, what we would call them voxels, LiDAR voxels, in the vicinity of this clearance gauge, and see in that way, if, example, vegetation is growing into the clearance gauge, and we could automatically generate a hint that there needs to be some vegetation management done. The other use for this is that this gives us a, so to say, a joker function. This is like an independent way of determining whether there's an obstacle in front of us. So the other functions you've seen are AI systems that are specifically trained to detect a certain type of object, such as a pedestrian, a train, a track. The system is trained to detect these. But with the occupancy detection, we have a mechanism that works regardless of what kind of object that is. So we can deal with unknown objects that way, or with unstructured objects, such as landslides or other things that may happen in an open environment. So this function really allows us to deal with any unknown obstacle that may we encounter during our train ride. This function was developed by ibeo, and you may also see this in their live stream on Thursday, and they're using the LiDAR system to compute this information. So we have 6 LiDAR scanners, as I mentioned, and they have different field of view. So we have a relatively wide field of view that doesn't extend so long, so just above 100 meters approximately. And we have a narrow field of view that goes up to 550 meters with this LiDAR.
Okay.
On the left, you can also
yeah.
see the statistics. I've also forgot to tell you. So we have a statistic for you on the dashboard to the left. You can see that we encountered more than 900 landmarks. We encountered 2 trains as I was speaking, and 34 pedestrians we had detected on our ride today in Hamburg. And for those that came in late, I want to mention again, you're seeing live data. So this computer graphics viewer that you're seeing is connected to the live data coming from our live ride in Hamburg that is happening right now.
Okay. And now we see all functions together. As you can see on the left-hand side, everything is marked red. So enjoy this nice view and this nice animation. And we are slowly coming to the end of our train ride, as we have just left Rotenburgsort and heading towards Berliner Tor. And we will sure have some time for questions from the audience. And I'm going to check the chat, Ruben, and ping some questions to you. One question was from Kai, and the question is, are there BIM or BIM models used for creating the landmarks?
Yeah, so in general, this process for creating the map can consume any CAD model, but we have, of course, specific requirements regarding the creation of the map. And using these BIM models would, of course, be very useful. Our experts can tell you exactly whether there were BIM models on the Hamburg track used or not. I cannot tell you right now whether this was the case or not. But in general, we are using a laser scanner and a reference location system that is highly accurate and generates centimeter precision maps. But yeah, the BIM model is, of course, a good hint. Yeah, thank you.
Okay. And also, if you have questions, you can post them on the LinkedIn event, and I will have a look there if you have questions and do not have account and access to the Twitch chat. Another question is from Sorgenkind. Are animals, for example, dogs, are also detectable, and what's the maximum range of the detectors?
Yeah, so they are detectable, and the range really depends on the size of the object. So if you take a dog as an example, it depends on the size of the dog at which we can detect him. Starting with the smallest dog, I would say we can still detect it at approximately 100 meters. But if it's a larger dog, maybe 150 meters, something like that. But we can also do this at night, which you cannot do as a human person. And so there are certain advantages also.
Okay. And another question is, how accurate are these features when going high speed, for example, 200 kilometers per hour?
Yeah, so these test cases we have done here, I'm not sure what you're referring to, if you're referring to the localization system or the perception system. So the localization system was tested here on using this S-Bahn. And we've shown you also the precision in a small window. So we have a 3 centimeter of lateral and 27 centimeter longitudinal positioning accuracy. So we think this is actually very good in comparison to what you can do with a normal railway positioning system that is much more in the range of many, many meters. With regards to the perception system, of course, there are also speed. Speed has an influence. But here again, we can just test this right now using the S-Bahn traffic that is speed limited. Obviously, it doesn't really go to 200 kilometers per hour as you've written. So I have to basically make you wait for any future projects where we can go faster with the train.
Okay. There is another question that has reached me from Roman Putter-Roussoff. I have a question, please. Are 550 meters of clearance enough for your use case?
Yeah, for the S-Bahn traffic, this is a sufficient range. And for other traffics, we may have to extend that range at approximately a kilometer.
And we just wanted to, again, let you know that this was a live train ride with passengers sitting in the train. So the guests from the ITS and a colleague of ours was driving the train. So because there were also a question on LinkedIn about that. So yeah, it was a live train ride under real conditions. I see we still have quite a lot of questions. Also a question from You'll Never Know. What tolerance is built in not have the train brake if a bird is crossing the green tunnel?
Yeah, so the design goal is to really have the same type of operation that you would have today. So you also react in the same way. For that, we need to give the system some capabilities in order to predict the behavior of dynamic objects and also to react differently to the type of the object and to the distance. This is very important.
Okay. And thank you. Another question from Blue Steel 911. What are you using for communication? GSM-R? How does the localization work in tunnels?
Yeah, so in tunnels, we do have some. First of all, we do always have a connection before we enter the tunnel, and then in the tunnel, we still have landmark information. We still have the radar detections. We still have the wheel encoder to propagate this. So we haven't tested this, obviously, on the Hamburg track for very, very long tunnels. So I cannot really give you a definitive answer whether the concept works for that as well. But this is, of course, one of the questions we will also address in this regard. With regards to GSM-R, GSM-R is today's standard, and the future standard is FRMCS. So FRMCS is our target.
Okay. Another question from Liwan Chin, I think. I wonder how much data is stored there in TB, terabyte. Thank you for this great presentation. Thank you.
Yeah, so that's an interesting question. I cannot tell you the exact number. I can tell you the train produces roughly 40 terabyte of data every day. And we are now planning to go on more extensively to collect much larger amounts of data. So then we speak about petabytes of data that we plan to collect. and improve the system with this data. So that's very important.
Okay. And another question from Roman has reached us. Does Deutsche Bahn trust to AI applied to railway applications requiring safety?
Yeah, so this is, of course, one of the hottest topics in safeguarding the use of AI for a safety critical application. And this is one of our work focuses in the perception group. And yeah, I can just tell you that we are on the edge, so to say, with the approaches we are doing. And other branches are also developing techniques there. And we are hopeful and optimistic that this can be solved, but it will also take some more time. So this is also why our project today is a demonstration, and our system is not yet taking over any responsibility in the railway operation yet. So this is a difference to our sister project. You may know we have a sister project, and they do automate just the ride itself. And there's a train driver who's basically still in charge. And so that is a system that doesn't need any AI and that can just that's basically ready for rollout. And our system needs an AI, and that's why it takes a little bit longer and also a lot more data.
Okay. Thank you, Ruben. And a question from Swanza. Can this technology be used to detect track condition?
It can. Now, we are not so to say, a specialized measurement train. So Deutsche Bahn has highly specialized vehicles for infrastructure inspection that are equipped with sensors just specialized to this measurement tasks. So we do not get down to that accuracy level with this system, because this system we are presenting is more for the general operation and track observation tasks. And so we cannot produce a super high precision that a very specialized system could produce. On the other hand, their system couldn't drive. So those are two different purposes. But we have the possibility to generate a lot of value here on a little bit more coarser scale.
Okay. Okay, I think we can take one more last question before we're coming to the end. It's from, I don't know, Clue. Are all the landmarks detected in across all sensor modalities?
So no, currently we detect the landmarks just using the LiDAR scanner. But as you've seen on the localization presentation, we also provide radar information to the localization system, and that is a different technique. So the landmark detection is basically classifying the surrounding. So we know this is a pillar, this is a wall. So this is classified information that is also stored in that way in a digital map. For the radar information, this is different. This is a so-called SLAM method. That's short for simultaneous localization and mapping. So basically the idea there is that you do a number of pre-recordings with your radar sensor installed, and you store all the reflections that you receive in a certain map layer. And then when you're live, you can look at that pre-recorded radar data and match it to the live radar data reflections you see on the train. And from there, you can produce that. So the camera does not yet play a role in that, but it's conceivable to also use that.
Okay, I think we are slowly coming to an end of today's event. And Ruben, could you maybe give us a little outlook? What are the next steps of the project? What are the upcoming challenges the project team is facing?
Yes, thank you. Of course, so we have come to this prototype that we now have, and we're really happy. And in the next phase, we would really like to start collecting more data, as this was a real challenge in the current project because of the short time that was available to do this project. And now we are looking forward with this functioning prototype to really start collecting data in all seasons and daylight and night in order to develop these functionalities further, complete them, and get them more mature. And this is really our next step that we want to do with our partners.
Okay, thank you very much. And yeah, for the end of today's event, if you would like to know more, if you are intrigued, you are invited to have a look at our Digitale Schiene Deutschland website. So if you would like to watch the animation again or tell your friends and family or colleagues about it, please feel free to share, and you can also follow us on LinkedIn to receive the latest news. And we also would like to highlight that we have 2 more streams upcoming. One is tomorrow at 3 p.m. hosted by Here, and the other one on Thursday at 3, hosted by ibeo, and our colleagues are very happy to welcome you there. So check it out and learn more if you like. And so far, thanks for joining. Thanks for being with us. Have a really nice day and see you soon. Bye-bye.
Bye-bye.